and when you subtract from the independent variable, it actually moves forward, and that's what we exactly did. If you see whether it should shift forward or backward, or right or left, it should shift right. Now it is very clear. If zeta is very, very small, then natural frequency and the damped natural frequency are almost the same. Now, what exactly you could expect in this part of the discussion under Laplace transform? Till far, we have been dealing with the Laplace transform of several functions. In fact, we also established the Laplace transform of a discontinuous function at t equal to 0, that is 1 by root t. Now we are going to look at the periodic functions. I did deliberate on the significance of the periodic functions and their Laplace transform, because every differential equation is a model of the system, and the system could be excited by any input, and that is where one of the excitations is the periodic function. Now, incidentally, we will also introduce a very important concept of time shifting, though we are not going to detail on it. Of course, the electronics engineers are going to pursue that at a great length. Right shifting, left shifting, upward and downward shifting. But here we give you a graphical idea of what exactly we mean by shifting of a signal, and also we will try and implement that while trying to derive an expression for the Laplace transform of periodic functions. Now, what do you mean by periodic function? You have already confronted several of them. For example, the simplest one you can think of, which you have pursued even at the pre-university level, is sine omega t. Now, if you are looking at the period of this, it would be 2 pi by omega. If you express omega in radians per second, this is in radians, of course, 2 pi, you will get so many seconds as the period. So, if omega were to be 1, okay, 1 radian per second, then the period would have been 2 pi. The moment you multiply t by a factor, then that is going to reduce your period. So that means that the frequency has increased, the period has decreased. That should be noted very, very carefully. For example, if I say sine omega t is one wave, 2 omega t, if I consider another wave, the frequency has doubled, the period has halved. That should be understood. Of course, these ideas are going to be rigorously visited again when you go to the discussion of Fourier series. But now let's come back and let us try and look at the expression for the Laplace transform of a periodic function. So the idea is as follows. We would incept with the standard integral of Laplace transform, which is 0 to infinity f of t e power minus st dt. Now this integral could be split into infinite number of integrals. And how do you do that? It is quite simple. At the pre-university level also you have done that for several functions. For example, if you are trying to get the area under this particular curve, mod of cos x minus sin x, for example. So what you have is one sine wave and also another cosine wave. So what happens from 0 to 45 degree, which is the leading wave, that is the cos wave. So you will get this area. So you will split the area under this particular curve into two integrals, that is from 0 to 45, that is pi by 4, you will have one integral, and from 45 to 90, that is pi by 2, you have the sine dominating. Then you will have another integral from pi by 4 to pi by 2. So this is split into two integrals. But of course the situation is slightly different, but here also we are integrating over several periods, because when I say infinite, I am integrating this integrand over several periods. So what I would do is I would integrate from 0 to 1t, and then t to 2t, 2t to 3t, like that up to infinity I will go. So how would I split the integral? It is as follows. That is, I would incept with 0 as the lower limit is, just like this, 0 to pi by 4 and pi by 4 to pi by 2. Similarly, I would start from 0 to t, and then this is f of t e power minus st dt, plus what would be the next integral? It would be from t to 2t, and f of t e power minus st dt, and this goes, you can have infinite number of integrals, because you see the upper limit is infinity. Now I will have to do a very, very important manipulation once I get these integrals in order to get an integral of this form, because I'm talking about a periodic function of period t. So I will have to establish my Laplace transform in terms of this integral. Let's try and do that. So what we have got essentially now is integral 0 to infinity f of t e power minus st dt is equal to several of those integrals. So let me write, and this goes on. Okay, so now let me say that this is from 0 to t. Now you can say what it is, t to 2t. Now you can say 2t to 3t. Now this becomes your lower limit again, 4t. It goes on. You can see that the difference between upper and lower limit is exactly 1t, right? Difference between upper and lower limit is 1t, and it is commonsensical that you know how to split a given integral. So the upper limit of the preceding integral will become the lower limit of the succeeding integral. Okay, so that is very, very important. Now let me consider an integral arbitrarily and then try and attempt the time shifting. So for example, if I consider an integral from t to tt, 2t, and then write the integrand, which is of course f of t e power minus st and then dt. So this integrand is being integrated from t to 2t, and I would like to shift the time so that you are going to integrate from 0 to t. How do you actually do that? Subsequently I'll give you a graphical visualization of what is going on, but now let's see how exactly it can be done. If I'm shifting it back, then I'm going to integrate from 0 to t, and what happens, I'm going to add, you're shifting back by one period, because this becomes 0, this becomes t, one period, so I'm going to add that period over here. I'll also reason out why I'm adding capital T to small t, and then e power minus st, how that is going to change, because there also you will have to change t, because once you change t here, every function that is there in the integrand must undergo change, right? So therefore what happens, e power minus s is absolutely all right, but inside the bracket what you should do is you should add t to that. Okay, so this is what is done, and then of course the order of integration is dt. Now what is very interesting to see, that this is a periodic function. Even if you add n periods, it remains periodic. The value will return to f of t. For example, if you take a sinusoidal function, what happens if I add 2 pi to that? Let us say t is measuring in the first quadrant. Let us say this is my t, and if I add 360 to this, it will come back to the same point. That means it returns to the same point. Even if you add n periods, it will come back to the same point. Do you observe that? This is the initial angle t, and if you add 2 pi, it will go one full circle and then comes back to the point of origination. And even if you add n integral periods, let us say n integral periods, it makes n circles and then comes back to the point of genesis or origination, right? So what I am trying to say here is, if you add any integral number of capital T to the small t, the function remains f of t only, right? So now let me simplify this and also give you what exactly I mean by shifting. So now before I help you visualize what is going on, first let me simplify this integral. So what we have got is 0 to t. Remember 0 to t because we shifted. As I said, the periodic function will become f of t whether you add any integral number of periods. So you can see this becomes f of t, but the exponential term is the one that is of interest to you. You will have minus st. This is my original exponential function. Now you have one extra term added, that is e power minus st. So if I take this out, e power minus st, if I take out, so my integral, that is when I split my integrals into several of them, I just considered the second one arbitrarily. Of course, first one is 0 to t. The second one I could reduce to this particular form. Okay, so this is capital T, small t, don't get confused. So this is the integral I was hoping to get 0 to t. The integrand is the same, but the limits are from 0 to t because I'm talking about a periodic signal. And if I'm able to do this for all the integrals, see, I could reduce this. If I'm able to reduce all the integrals up to infinity, then my job is done. Then I can have this integral, and plus if I add up all such coefficients that I'm going to get, then I will be able to get my expression for the Laplace transform of the periodic function. That apart, now this is understood. So let me walk you through what exactly I did, and then I'll give you the graphical visualization. All that I did is I shifted this entire integral because it was by a period. It was from t to 2t. When I shifted left, what happened? The limits of the integral became 0 to t. You see here, if you shift by one period, instead of t to 2t, it is 0 to t. And in order to shift to the left, what I should do, I should add that period by which I am shifting, which will be clearer in a while, to small t. And the same thing must be added to the t in the exponential function, and this becomes f of t, and this exponential function gets simplified, rather gets split into these two components. They multiply each other because when you have two exponential functions and multiply each other, the powers get added, commonsensical, right? So what happens, this power e power minus st is the one that you have introduced newly because you added t to this small t, and that is taken out, and the rest of the integrand is what it was. And now the limits are, instead of t to 2t, it is 0 to t. So whether this is applicable to all the integrals, we'll check out, but we shall visualize the process what we did right now mathematically. Now here, in order to help you visualize what is going on, I have considered a very, very basic function, that is a very, very low damping, because I want the period of this wave to be almost 2 pi, right? The reason being, when you actually introduce damping, your period would be, instead of 2 pi by omega, this is the natural frequency, that is the coefficient of sine, assuming that there is no exponential term. This which we have been seeing, I have only attached n as suffix, emphasizing that the natural frequency. But when you have an exponential function, that is the damping associated with the system, the period in fact becomes 2 pi by omega damping, which is 1 minus zeta square, assuming under damping. So this becomes my period. When zeta is, which is the damping ratio, is made very, very small, which is the coefficient of x here, okay, assuming it to be very, very small, the period is approximately 2 pi by omega. Okay, so the period almost remains 2 pi because here omega n is assumed to be 1. Okay, almost 1, because here also the damping frequency is made almost equal to n, because your damping ratio is very, very small. So let's see what exactly happens. So the first wave that I'm talking about is the blue wave. And what you should see here very, very carefully, as the wave is moving, what is happening is it is losing its amplitude. It is losing its amplitude because it is getting underdamped. But the loss of amplitude is not very, very significant, but it is definitely happening. Over a period, it is losing amplitude. It's a damped oscillation. But I have also considered one more signal where I have subtracted the period. This is the approximate period, because it's a damped oscillation. This is not the exact period, approximate period. So which I said, when the damping ratio is very, very small, the period is almost equal to the period that you find in an undamped situation. Now, I told you two things. You can either subtract the period or add the period. If you add the period, the wave would get shifted left. But if you subtract the period, the wave gets shifted forward. That's very important. If you add, to make that very, very clear, I'll give you a very trivial example here. Let's say that you are talking about the mod function. Y is equal to mod x. Understand this carefully. If I add 1 to the x, then what happens? The mod function gets shifted. That is, I am talking about y equal to mod x plus 1. That is, if you add 1, what happens? It gets shifted to the left. If you want this to be shifted to the right, what happens? You will have to subtract 1. So the mod function gets shifted forwards. And if you consider mod of x plus 1, that is, you are adding, then what happens? Obviously, it gets shifted to the left. It's commonsensical to make it out, because if you put, if you want a y to be 0, x minus 1 to be 0, then obviously this is a point x equal to 1. And if you want to see where exactly y is going to 0, x plus 1 is equal to 0, that means it is x equal to minus 1. So it is very clear that when you add to the independent variable, it gets shifted back. And when you subtract from the independent variable, it actually moves forward. And that's what we exactly did. If you see what we did here, we in fact added t so that it could be shifted back. See, it was from t to 2t. Now we shifted from t to 2t to 0 to t, and therefore we had to add t. That is very, very important. And that is made very, very clear in this particular example. You can see when I added, it actually moved back, and when I subtracted, it moved forward, right? So this is very, very easy to visualize, and this is what exactly happening here. See, look at this damped sine wave. I would call this damped sine wave. What is happening here is, the moment I subtract, whether it should shift forward or backward, or right or left, it should shift right. Now it is very clear. Whenever you are actually subtracting, it should shift right, and whenever you are adding, it should shift left, right? So left shifting or right shifting is decided by whether you are adding or subtracting, right? Here what I have done, I have approximately assumed the period to be 6.28, that is 2 pi, which is actually not the case, because it can be slightly here and there, 5%, because there is some amount of damping, but the damping is very, very low. So what we are trying to impress upon you here is, observe this carefully. Because you have subtracted the period, almost the period, then what happens? The entire wave is shifted to the right. The entire wave is shifted to the right. So what you can see is how you are observing this. It's very tricky to do so, because you can see the amplitude over here. What amplitude this blue wave, I mean, if I consider an interval of 2 pi, what amplitude this blue wave had, 2 pi interval back, that is 2 pi radians before, the red wave is going to have the same amplitude after 2 pi radians. Say approximately this is one point, this is another point, which are 2 pi radians apart. If you say, then the whatever the amplitude that the blue wave had, that is before 2 pi radians, the red wave has the same amplitude after 2 pi radians. That means this damped wave is simply pushed forward, right? It is losing amplitude. It had so much of amplitude, that is 2 pi radians before, but the amplitude here after 2 pi radians has actually decreased. You can see here, it has actually decreased. But red wave is going to have the same amplitude after 2 pi radians. That means it has been literally pushed forward. It has been pushed forward, and this what you are seeing is right shifting, because all that I have done is I have actually subtracted the period from both x. You can see this for any wave, whether it is the period or not. If you subtract from the independent variable, then what happens? That function gets pushed forward to the right, and if you add, it gets pushed backward. That is very, very important. So this is just a high school way of visualizing what is going on. Since we had exponential and a periodic function, I chose this particular idea to help you visualize what is going on. So now, having understood this, now let's consider our original integral, which was split into infinite number of integrals. Let us see how it can be manipulated now. E power minus st f of t dt, this is equal to 0 to t f of t e power minus st dt. This is all right. But what about the second one? We did prove that it is e power minus capital st. S is of course the same. T becomes capital. 0 to t, instead of 2t to 3t, rather t to 2t, rather t to 2t, it becomes this, that is f of t e power minus st dt, right? So can we actually do the same thing for the next integral? What limits it would have? It would have the limits, since it was t to 2t, this will be 2t to 3t, right? This would have the limits 2t to 3t, and therefore this would could again be reduced. This could again be reduced. That is, it can be shifted by 2 periods. It can be shifted by 2 periods. So therefore, what would happen with that? So if you shift it by 2 periods, it will become 0 to t, because you are shifting it by 2 periods. F of t plus 2t, t plus 2t, because look at the limits, you are actually moving to the left, right? You are adding 2 periods. And what about e power minus s? And this t is also going to be replaced by 2t, also going to be replaced by 2t, right? So what happens? This again gets, but this is of course f of t, because it's a periodic function. You are adding 2 periods. This is f of t. What happens to this? If in order to retain the same integrand as we do, we will have to take e power minus s to t outside. So that means I can rewrite it as e power minus 2st to st, and then integral 0 to t f of t e power minus st dt. See, for the second one, you have got e power minus 2st. First one, it was e power minus st. So this keeps growing by 1 every time, right? For every integral, you have infinite number of integrals. So how can I recast this? So let me tell you what exactly happened till far. What we said is, we reduced the integral t to 2t by adding 1 period, so that it was shifted to the left, and 0 to t, from 0 to t, instead of from t to 2t, it was shifted by 1 period, 0 to t. And as a consequence, what happened? We could get a coefficient. You can see here, we could get a coefficient e power minus st for the second term. For the third term, what coefficient we could get? For the third term, we could get e power minus 2st. Fourth term, e power minus 3st. Fifth term, e power minus 4st. It goes on like that, right? So therefore, can I categorically write now that my integral 0 to infinity f of t e power minus st dt, this is my Laplace transform of f of t, which is a periodic function, is now going to be, so 0 to t, first one will have coefficient 1, e power minus st f of t dt, doesn't matter which order you write f of t and e power minus st, and the second integral would have e power minus st, the integral, and then blah blah blah, the third integral e power minus 2st, and this goes on infinite for infinite number of terms. So what I can do, I can take this as common factor, that is 0 to t e power minus st f of t as common factor, and then inside the bracket, for the first integral there is coefficient 1, for the second integral there is coefficient e power minus st, for the third integral e power minus 2st, okay. For the fourth, this is for the third, for the fourth integral it would be e power minus 3st, and it goes up to infinity. So this is a geometric progression where r is equal to e power minus st, where r equal to e power minus st. Just compare that, 1 plus r square up to infinity, right? This is a typical geometric series. This is of course 1 by e power st, that means it is less than 1, and it is going up to infinity. So therefore, for an infinite series geometric progression whose r is less than 1, the sum is given by the initial term divided by 1 minus common ratio. Initial term 1 minus common ratio. Of course, when n tends to infinity, the standard formula, sum formula for geometric progression reduces to this. You can look up for this formula in our PDF. So therefore, this entire thing can be reduced to this, which is nothing but 1 divided by 1 minus e power minus st, because r is this, correct? R is this. So therefore, what is the formula for the Laplace transform of the periodic function? Now it is very, very categorical. The Laplace transform for the periodic function is simply given by 1 minus e power minus st and integral 0 to t, where t is the period, f of t e power minus st dt, right? So this you should not forget. If the periodic function has two components, then of course you will be splitting this integral. For example, if you are looking at a triangular wave from here to here, you will have one integral, and this point to this point you will have another integral. But of course that is as far as this integral is concerned, but this remains a constant coefficient for both, because this is for the period t of the periodic function. So this is the formula that we are going to use and deduce the Laplace transform of periodic functions, any periodic function. So this coefficient is going to remain, but depending on the definition of f of t for a periodic signal, this integral may be split into two integrals, in your case at least, university problems that you confront. So let me walk you through the entire discussion, what exactly transpired, and clear some of the ideas. Now we started with the idea of the periodic function, and one of the periodic functions that you have always confronted is sine or cosine with period 2 pi. The moment you multiply that by omega, earlier we can consider the omega to be 1 radian per second, but here it is 2 pi by omega, that becomes your period, and as the coefficient becomes coefficient greater than 1, then the period decreases, the frequency increases. the moment you double it, for example here, the frequency doubles, the period halves. And also I told you how to split a definite integral, because an integral which is considered from 0 to pi by 2, for example, for modulus of cos minus sine, is split as per the convenience, because from 0 to pi by 4 cos is leading. You can see the cos is leading. From pi by 4 to pi by 2 sine is leading. So therefore it is cos minus sine x from 0 to pi by 4, and from pi by 4 to pi by 2 you can have sine minus cos. This is just to tell you how the integral is split in order to accommodate the overall limit. So here the overall limit is 0 to infinity, so that can be split from 0 to t and t to 2t. What is very very important for you to observe is that the upper limit of the preceding integral becomes the lower limit of the succeeding integral. And what we have essentially done is we have considered all integrals across a period length of t. That means lower limit is t, the upper limit is lower limit plus 1t, right? So that is how we have considered, and you can clearly see that 0 to t, t to 2t, 2t to 3t, 3t to 4t, infinite number of periods, because the original limit is from 0 to infinity. Now what we have essentially done here is that we have used two concepts. If you add integral number of periods to any periodic function, you get back to this periodic function. I gave you the example of sine t. If you add any number of 2 pi's, it will circle so many number of times. For each circle it is 2 pi radians, and it comes back to the point of origination. So that is what we have used, and we have considered the first, of course the first integral is from 0 to t, the second integral from t to 2t, and we wanted to shift left, that is by a period t. So what happens if you shift left by a period t? The original limits of integration are from t to 2t. When you shift left, it is from 0 to t, because you are shifting exactly by one period. That means the lower limit becomes 0, the upper limit becomes t. And in order to do that, in order to do the left shifting, you will have to add one period to the independent variable small t here for all the terms involved, the exponential as well as the periodic function that you are talking about here. So when I did that, what happens? I get this particular extra term e power minus s capital T, because you can clearly see here that t plus t I have replaced t by. So when you multiply inside, you get my e power minus st, and then one more extra term, that is e power minus s capital T, and that is the one that you are getting extra, because this is the integrand that you started with. So this is one extra term that you have taken out, and we told you how exactly the shifting happens. When you subtract, it gets shifted to the right, and when you add, it gets shifted to the left. And here I gave you the idea of shifting by considering a sinusoidal function multiplied by a decaying function, where I assumed certain damping, and the damping is so slow that the damped natural frequency is approximately equal to the natural frequency. That is, this is the damped natural frequency. If zeta is the damping ratio, if zeta is very very small, then natural frequency and the damped natural frequency are almost the same, right? So this is the damped natural frequency. Note omega n into root of 1 minus zeta square, and this is the natural frequency. And here you can see that the wave is losing amplitude as it is moving. And one way to very categorically tell you how the shifting of the wave has happened to the right by subtracting the approximate period is that whatever amplitude the blue wave had 2 pi radians before, you can see this is being possessed by the red wave after 2 pi radians. After 2 pi radians, you can see the blue wave has lost the amplitude, but the same amplitude is there with the red. Of course, both the waves are losing amplitude, but the amplitude that was 2 pi radians before, that is the history of blue, is the presence or present situation of the red wave, right? So therefore it is very clear that the red wave is shifted or pushed 2 pi radians forward approximately. Of course we have made these calculations numerically approximately just for visualization. So you cannot say it is exactly 2 pi, around that particular factor. And you can see that we have shifted period for every other integral. The integral which had the limits from 2t to 2t in fact has this coefficient. And if you observe carefully, we have also reduced the fact that if the integral had the limits t to 3t, then what happens? It will have a coefficient of e power minus 2st. Remember, this exactly goes with the lower limit, because when you shift by so many number of periods, the lower limit is becoming 0, and whatever coefficient you are getting, that has the lower limit multiplied by minus s. E power lower limit multiplied by minus s. So that is where you are getting the coefficient, and knowing that it is going to increase by one period for all the rest of the integrals, you get an infinite geometric series whose sum is given by initial term 1 minus the common ratio, that is r. Common ratio here is e power minus st, because every time you multiply an exponential function by e power minus st, the power augments by 1. Remember that. So therefore we have got this, and when I substitute all of this in the final expression, because this integral becomes common for all, if you take out, and this is the sum of the geometric series, infinite geometric series, so you will get this, and this remains constant for all the periodic waves, because this is the period, this is yes, this is a constant. But this inside integrand definition, that is the integrand, can have different definitions. I gave you the example of a triangular wave. So the first half could have one definition, and the second half could have another definition. So this is the standard formula for a periodic function of the Laplace transform of a periodic function, right? So with that, let us wrap this discussion and get to problem solving of typical university situations. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.